If I could, just my name is Jon Davis. This is Bob Henley. We're with ADACEN Corporation, and we're a company that's headquartered out in Albuquerque, New Mexico. And I think we're ushering in kind of the next generation of technology to enable the data center industry to basically meet the demands of the customer, right? I'll tell you right up front that I was a Marine aviator for a long time, 37 years, retired as a 3-star. Uniquely, I would commanded our Top Gun school, the Moss 1, our weapons school in Yuma, Arizona.
I guess I don't need to introduce you.
Yeah, you don't. Yeah. You didn't tell me you can do that, so I'll do it myself. Yeah, Yuma, Arizona, and I got sent to Fort Meade, Maryland, to go stand up a thing called Joint Functional Component Command, Network Warfare, and into my world at NSA in the national security intelligence realm, and then did that for 2.5 years. Went back, commanded an air wing, and got brought back as a 3-star to be the deputy commander for the United States Air Command. Did that, went back after that, went to be ran Marine Corps Aviation for 3 years, retired, and went to work living out in Idaho and basically some board work. But a little over 2 years ago, Bob and his gang called me and said, "Hey, we're looking for somebody with your background who can help us grow the company." And I looked at the idea and I said, honestly, knowing what I know about our data centers and how unprotected they are, and how much we rely on our data centers in a digital economy, how much power they draw. I said, what these guys showed me was, honestly, I said, this is a brilliant idea. And I checked with some of my friends at Fort Meade, had them validate the concept, and they said, it's a very, very secure environment. Frankly, ADACEN's all about resiliency, right? Resilient power, resilient locations, and quantum safe encryption, identifying all the ways that data could be interdicted and not be resilient, and making that more resilient. And one of the things that we came on, Bob and his team came on, is how much power a data center pulls and how much power you need to cool the servers and the storage is actually really, if you could have less of a draw on that, it actually makes that data center more resilient. Okay, how much power you provision for that? So we were thinking about, making a very resilient spot, a place that we could, because we're provisioning not only primary power but backup power for that data center. The data center always gets fed first. We devolve to the grid, vice from the grid. And so the power efficiency of the data center is really important to us. We first looked with 2-phase liquid immersion, which is really complex, really expensive. It has some toxic fluids in there that not very environmentally friendly. About 2 years ago, we came on a single-phase immersion system, single-phase immersion, that we have adopted and are championing now for the last 2 years. And honestly, it's delivering incredible capabilities that Bob is going to talk to you about today. How did we end up here? The Eisenbergs up there running a little UAV company. I help out little companies go get stuff like that, or at least introduce them to people where they can go do the things they got to do. I talked with Marcy and her husband up there, and they looked at it. I said, well, I'd love to put one of our immersion pods up here for data storage up at your UAV facility. And they looked at the technology and they go, hey, this is brilliant. Have you thought about talking to Loudoun County? Because we have a problem here. We're out of power. Right? I know we've been tracking that. We came in here early. Like we came here 2 years ago, and my first trip was out to the data centers around Loudoun County. Like we knew we had a solution for Loudoun County. It's a matter of time when Loudoun County comes to it, but it's the only way you're going to be able to grow with a finite power supply in order to grow your capability. And Bob's going to talk to you about that. But we looked at that 2 years ago, how we could help do it. Our solution uses 40% less power for the same computer. We use 1/10 the space. We use 0 water. So all the cooling is that there's no water manifolds. All the cooling, it's a self-contained unit. So we're not pulling water out of an aquifer. It's basically, I would call it, I'm not a technologist, Bob is. It's like a dielectric fluid vegetable oil, right? All the compute goes into the vegetable oil, the fluid. That's where it does all its cooling. There are no air conditioners associated with our system. We use air handlers only, right? You don't need it. They generate no noise. They don't generate a lot of heat, right? The heat is dissipated outside like an air handler in your house at a 4-amp circuit. So it's very, very energy efficient. What's also, it's allowing technology we employ, not only is allow 40% less energy, we've been doing that now for 13 months and improving that, It's also that the industry's already moving this way. The server blades we're getting now have no fans in them. No fans. They're building without, they're loading up those server blades with CPUs and GPUs that Bob will talk about, more and more capacity. And this fluid that we've put our blades in is actually doing a really great job of dissipating heat. What that also allows is most of the computer blades are running up towards 200 degrees Fahrenheit right now. And most people have to pull the power off those blades. We're running them 24/7 full out. We're not overclocking anything, but we're running them 24/7, frankly, and the temperature's not a problem. And Bob can tell you exactly what Johnny said. This technology works. It's not fairy dust. It works right now. We've been doing it for 13 months out in Albuquerque, New Mexico. We're also standing up the next data center in Silver Spring, Maryland. And our first pod's been moved in up there now. So we're going to talk to you about the technology. Bob is. If you're ready for that, Bob. But it's honestly, it's really simple, but it really works well, and frankly, it's the future for the data center industry. It will allow you to grow your business by, if you're captive power right now, you could actually do 40% more. And I know that was the thing we talked about, Scott, about, hey, it's important for our revenue, our tax base as a county. We can't grow it anymore. And so they're going to go other places where they can find power. That's what's happening. Or you find a way to compel your data center operators to adopt the new technology, get their customers to adopt the new technology, and they can do 40% more of the power they have right now.
Is it retrofittable?
As we call it immersion conversion, 100%. It's, again, Bob will show you how easy it is, all right? It's so easy a Marine can understand it. Bob?
And Bob,
Don't say that around my father.
I queued up, so just let me know when you want to ask.
Well, first of all, thank you, Jon Davis, for that introduction, and thank you all for getting together today. By the way, he's from San Juan, Idaho, or he lives out there. Our facility headquarters is Albuquerque, New Mexico, but I'm a local. I've been in the Washington D.C. metro area for the last 30 years, and I see all these pictures of Dallas. I just dropped my daughter off. She's going back to Moose Jaw, Canada, early yesterday morning. So a very big fan of the area, big fan of Loudoun County, big fan of the economic development that was done here. I used to be with a company called US Internetworking out of Annapolis, which was one of the first application service providers. And that was back in 2000. And that's about when everything started happening out here, you know, cows to computers, right, as I used to say. And I've just been amazed at the growth and all that. It's not a competitive environment that we're created against what Loudoun County has. It's a cooperative environment. We created this data oasis concept. ADACEN stands for Advanced Data Centers. We created that specifically because we needed to find a place where we could be a little bit more resilient than sort of a standard commercial data center in a commercial business park. Again, for convenience, for proximity, for low latency, it all makes sense. You have to have trading data centers in Secaucus, New Jersey for Wall Street. You've got to have, you know, with all the internet exchange that's here in Loudoun County, the mecca of it all, if you will, you've got to have these data centers close to that connectivity. So it all begets the right kind of model. We're not doing anything to compete with that. Like I said, the collaboration is when somebody says, I need to have a defendable facility that's military grade. That's why we're building facilities on military bases. That's why we have things like air gap data for moving data over aircraft. That's why we have resilient power. You heard Jon Davis mention something that was really subtle, but instead of failing from the grid, we fail to the grid, which means our campuses are large enough, we're building our own power systems to power the data centers. That's what really differentiates what we're doing. But what we found was we're in a really hard spot when we're in the high desert and out in the Southwest and Midwest, where there isn't a lot of power and there isn't a lot of water. So we just said, how can we take sort of a fresh approach at a data center capability if what we really wanted was this resilient power, this resilient physical security, controlled airspace, in some cases absolutely the highest controlled airspace in the country. What are we going to do from a data center perspective? Do we build the traditional air-cooled units, the traditional raised floor environments, traditional liquid and air-cooled systems, and the cost of those and the size of those? Typical 100,000 square foot facility, 10 megawatts, $100 million before you put your first server in there. Well, we started looking at the liquid immersion environment, which, by the way, the technology isn't new. It's well over 10 years old. But what's really made it prominent in our mind is the simplicity of it, but also the right sizing of it today based on server manufacturers coming out with higher and higher and higher density servers. You go from a couple hundred watts per CPU chip to now 500 watts to almost 750 watts to nearly 1,000 watts on GPU and CPUs. You just can't cool that with air anymore. It's becoming really impractical. we decided that instead of guessing, we would do everything we were gonna do and test it with national laboratories. So whether it's Sandia National Labs, whether it's Los Alamos, whether it's the National Renewable Energy Lab, we started testing all these systems and services and capabilities and said, is it really a problem, air cooling, high density, high performance servers? And the answer is yes. Newer and newer types of storage is actually getting hotter. The old spindle drives, you know, I call them old and legacy or traditional spindle drives, spinning disk, hard disks, didn't use a lot of, generate a lot of heat, but they use a lot of space. And then there's a lot of what's called reading and writing, so the performance isn't really good. Now a lot of folks are adopting this solid state storage, which is basically like a memory chip, like a USB drive. And when you take all that and you shove that into a small area, now you start generating heat like you do with servers. And so it's like, oh, now there's a problem. So we wanted to solve all those problems. We wanted to use a simpler building. If we're building on military bases, we don't want to build traditional high, you know, for air ventilation data centers. We want to use something like, say, a hangar. Very simple building. What can we do and how can we build something at $200 a square foot versus $1,200 to $1,500 a square foot? Not all that complexity for air cooling, not all the components that could fail. So simplicity begets resilience, begets a smaller footprint, and the liquid immersion environment that we decided to adopt really changed this. So we have sort of the width of what we do is the pre-grid power, the physical security, and the enhanced networking capabilities, including air gap flying data on aircraft. But then the depth to it is efficiency. And that efficiency is really what we're here to talk about, which is how we were able to create PUEs of 1.02. In the data center industry, that's sort of the mecca of all standards, right? Your power utilization effectiveness. If it takes 100% of your power to power servers and it takes another 50% more power to cool that environment, that's a 1.5 PUE. It takes 50% in order to cool that 100% environment. What we're able to do is use 2% of the electricity to power our servers to actually cool the environment entirely. So our PUEs are 33% less. That means our power consumption is 33% less for the exact same server environment. Now you add really high density servers to that. You add them in a very small space. And in the traditional data centers, like a lot of the ones around here, not the hyperscalers, but I'll call it a traditional data center, they use those sort of kind of the 5 or 10 kilowatt per rack model, kind of a standard power distribution, standard rack model. Luckily enough, here in Loudoun County, you guys have a lot of hyperscalers that have 50, 60, and 70 kilowatt per rack models. They take a lot of power though. There might be a 1.6 PUE. 60 or 70% more power is required to cool the environment. We're able to do 100 kilowatts per pod, which is the standard size of a regular rack on its side, and do that at a PUE of 1.02. So 10 times the density, 1/10 the space, that's an order of magnitude in both directions, at a third less power. When we build our facilities, we standardized on this, and we found we can do an equivalent of an 80 rack environment in 4 of these pods and do that 400 kW with that 1.02 PUE. That's just, these are numbers that are staggering in terms of cost savings, efficiency savings. The problem though is the adoption. If you have a traditional data center company that's a REIT, they want to sell space and power. When you tell somebody you can save them space and power, they go, oh, that's what I sell.
Right.
Until you're out of one of those things. Now all of a sudden you start to get their attention. So this is the right time to bring this up. Before it was counterproductive to bring it up into a REIT's environment because they're like, oh, I want to sell more power. Somebody's willing to buy it, I'm willing to sell it. But if it's not there, now the question is how can you get more use out of that facility?
There's other places now, it's power, space, and water. Albuquerque, Africa, where we've been doing some work, they don't have water spare. And frankly, a lot of the get the new kind of compute, basically get to operate the temperatures, we have water manifolds, and they're pulling water out of the aquifer. And now the Facebook's got a facility out in Albuquerque, 6-building facility with solar power, so they got all the power they need, but they're pulling water to cool their servers. And frankly, the farmers are complaining. They've only built 4 of the 6 facilities because they're out of, not power, water.
Multi-100 million gallon water consumption, and they've depleted their welcome. They gave schools away, they gave firehouses away as part of the community development, which was great, but now the relationship's over when there's no water left for the farmers. And they're just going, what is wrong with this? So another unique thing about what we're doing is we're working closely with the federal government sides and Department of Energy to look at how we can help modernize Department of Energy facilities. There's 2,700 data centers throughout Department of Energy, and to be able to solve
Thank you.
and share and shave a third of the power off of that is huge. To be able to save no water use is huge. And so, you know, we're not here to really sell a product, we're just letting you know what we've done differently to create an awful lot of efficiency within an environment in which we use less power, less water, less space, less complexity, which gives us the higher resilience. Ultimately, that's why we did it. And we're converting right now. We've got some agencies that have been talking to us and saying, we appreciate what you're doing in your facilities, but we already have our own facilities, but we're out of room, we're out of power, we can't use any more water. And we're like, well, if we do this immersion conversion in the existing environment, whether it's a raised floor or not, we can still convert these environments to much more efficient environments. That begets the higher performance servers. Now there's a lot more things like artificial intelligence, machine learning, modeling, simulation, all that stuff is now very practical in this very small environment. To the point now where I think they see one of these things, there's even these micro versions of these data centers. Literally a data center in a box that has the same liquid immersion capability and can be put out at the edge. You're gonna start seeing these at cell phone towers, you're gonna see these in utility substations, because that's what we're doing, and you're gonna start seeing a lot more edge compute because of things like this, a complete NEMA 4 enclosure, outdoor rated capability, you know, right at the edge with ultra high performance compute in a very, very small space. That's a micro version of what I just talked about, the cooling, the immersion, the high performance servers, the software, all that stuff now can go in a very, very small compact arena. Then take that and scale that to the facilities that are here, and it's mind blowing what you can get efficiently and savings wise. So we've spit a lot of stuff out here.
Yeah.
Questions before we sort of show you some of this stuff?
Isn't the water used, isn't it recycled somehow? I mean,
So think of a
it doesn't go away, right?
closed loop.
Yeah.
So the immersion tanks are liquid. They're a synthetically created, I'll call it like a cooking oil, of the viscosity of a cooking oil.
Right.
The single phase immersion stuff that we're using is not a biohazard. There's no MSDS material sheet for hazards. There's no hazardous labels on the containers. You can actually ingest it. I don't recommend it because it just tastes like oil, but you can ingest it. It doesn't evaporate, and it's just a 15-year design life. And this stuff, from most of the manufacturers, it's a 10-year warranty. So it's really simple. It doesn't evaporate, but it also never leaves a tank. These immersion tanks, they just cycle it with a pump system to create a vortex of heat flow. There's a radiator inside the tanks, and then there's a closed loop. In our Albuquerque facility, for every 4 pods, we have a closed loop system of 1,000 gallons, and that's a 60-40 water glycol. And it's closed, and it's sealed. And we even put a pressure tank against it, so we have a solid system, so there's no water falling effect, there's no cavitation. And so we have a nice closed loop system with a pressure tank, 1,000 gallons. It's only 75 gallons per minute flow, very low, and only 20 pounds of pressure. It doesn't need a lot of anything. So it's really simple, and it's really easy to maintain. With the pressure tank, the pumps being 1 amp, the dry cooler that we use is basically like in your car, it's a radiator with 2 electric fans. And we use 480 volts at a very low current. So again, we get efficiency there. And when you add up the CDU, which is the cooling distribution unit, that's the cycling unit in the tank, the pumps for the 1,000 gallon loop, and the 2 fans on the dry cooler, you're at 2% of the utilization that the tank can handle in terms of its server load. And then when you measure all that, and you look at it real time, temperature sensors, controls, all those types of things, we're using like a 1.008, 1.0, 10. We get up to, on our worst day, a 1.02, when we're doing 100 kW per pod dissipation. And we do those in increments of 4. So you could outfit a facility very, very easily. The Silver Spring facility that Jon Davis is talking about is an existing air-cooled facility that has its own crack units and loops and all that, and we're just simply tapping into that. We need an 8-degree differential between our nominal temperature, which we keep at 90 degrees. We don't keep the tank really hot. Servers never go over about 115. The CPUs, it's just crazy running wide open. I don't care what Hypertech, a 2CSI, a Gigabyte, a Dell, an HP, we can't get those things running 100% duty cycle over 115, 120 degrees at the CPU. Our tank's nominally at about 90 degrees. Our loop only has to be 82. Most data centers are running 45. So now you start to see huge economics of less energy capabilities or requirements. So even converting an existing data center could actually let the temperature come up a bit. and not have to keep it all that really cold and that low, because you're not transitioning that much heat dissipation in air.
Well, I'm really worried about the trade craft, about especially HVAC systems. And when everybody talks about data centers, I used to always say, what's a data center? And people would tell me that, they push ones and zeros through these fiber optic cables. And I said, no, it's a big refrigerator. Because basically that's what
It's
you
an
need.
oven that needs a refrigerator.
Yeah,
Yeah.
that's what you need to
In water.
initially. Now, that's true HVAC. Is this system more technical requirements than a normal HVAC system?
Yeah, well, a lot less.
So look at your car. I'll use a perfect analogy as a car. You have an engine block. It generates heat from combustion.
Right.
You have a water loop in there, and maybe glycol, right, so it doesn't freeze.
Mhm.
You have a thermostat. Then you have a radiator, and while you're driving down the road, the airflow over the radiator is enough to do the heat exchange. Look how simple that system is. And the thermostat just regulates the temperature, right? That's really all there is to it. Well, now if you're stopped, what happens? There's no airflow over the radiator, so you have like electric fans nowadays. You used to have a fan belt and a big fan, and it would make all that noise, right? The old Buicks and you name it,
I still do
back in our
my
day. Yeah. So if you don't have fan belts and all that, you have electric fans, and they come on automatically when needed. We'll take that same system now, and instead of it being an engine block, now it's a tank with liquid in it that's pulling heat off of servers. And then inside there's a circulation pump that all it does is it keeps the hottest fluid, which is up the top, keeps the hottest fluid over a radiator, pulls the heat off. Now you have that same loop that's just like in your car. It's that simple. It is not complex at all. And it's really easy to maintain. And quite frankly, the fluid has enough heat dissipation capability for you to get to the critical load of a server, like 225 degrees, where they start to degrade in performance. That might take a day. So now you don't have we have a down system, we've got to hurry, we've got an hour before things start to, you can run it probably a good day in a 100 kW tank before you have to worry about it getting to a critical temperature. It's got that kind of heat dissipation capability.
When you watch this, so Bob's gonna show you a picture of the tanks. There's 3 different sizes of them. But it's almost like a freezer on the deck with a lid that opens up. It's a server lying on its side with the fluid in there. There's a pump, generally one pump on one side. And you think about it like a fish tank. Fish tank's pump's always running. This thing only comes on, the pump only comes on every once in a while. Just when it needs it. We have these little rubber ducks we put up on there because if you didn't see the pump running, you wouldn't know it's running. So it doesn't make really much noise. And so you can just see this little duck start to flow towards the intake at the back of the pump. And then outside, we live Albuquerque, it gets pretty hot in the summertime. You can go in the room right now. If we had our 4 pods in this room here, that's an 80 vertical rack equivalent. The level of noise is about what we have right here, nothing. So you could actually have your meeting on top of that. My ears aren't doing real well after 37 years of flying jets in the Marine Corps. And I come out of a data center and I have the ringing in the ears, and it's just 10 times worse after even doing a quick pass through a server room. There's no noise. There's no real heat coming up out of the pods. It's going outside. Each pod is connected to 2 pods connected to 1 air handler fan. Like Bob said, think about the fan on the back of a radiator. It comes on episodically, every once in a while when it needs to, not on all the time. I mean, it's a very, very rugged, reliable, simple system.
Well, also, some people say data centers don't have a lot of people, and so we're here in protection, and they're loud, that's not a big deal, there's not that many people affected by it, but now you start thinking about, we could have a data center in this room while we're talking. This is what he was talking about, so having the ability to push this stuff out to the edge is really important. For government clients and intelligence community clients, this is really important to be able to have this edge compute capability pretty much anywhere. The ruggedness of them, to be able to put them in substations, to be able to put them in cell phone towers, to be able to put them on the roof of the building, literally outside. That's where this is all going.
The law firm in San Juanito is putting one of those micropods upstairs in their 3rd floor of their building, and basically move all their compute, all their storage into one small device. And they'll also get a private cloud associated with that too.
If I may, we just have one question back here.
Yes.
And if we go through the slides.
Yes.
Great.
Quick question, is it financially feasible for existing data centers to implement your technology?
Yes, it is, because these tanks are really not that expensive. If you already have the sunk cost of a chili bloom system, then you're just tapping into that. You can actually raise the temperature of that, so you even have more efficient use of that system. You don't have to cool as much, you now have to just cool a little bit. And so there's more capacity as a result of being able to do that. If you take a chilled loop and take it down to 45 degrees, and now I say you only have to take it down to 82, people laugh at me and go, well, you don't even have to cool to do 82 with just the radiator effect on the chillers outside. When you do adiabatic and start using water, that's when you have to really get it down low. You don't require any of that, because we only have to get down 8 degrees below the 90-degree set point that we want to use. And we can go a different temperature range from that, but it makes it so much simpler to use the system that's available. But if you're building from scratch, quite frankly, you don't need any of that. You just need the dry cooler, which is nothing more than a radiator and fans. And in the worst situations, with the highest density compute, you can use water misting if you really need to on a case-by-case basis, but we have not used that ever yet. And we're in the high desert of California, in New Mexico, where it's 100 and some degrees and it's 6,000 feet. If there's any place we're gonna need adiabatic cooling, it would be those locations. And to this day, they've never come on. We've wasted our money putting those systems in. It's really a game changing. I'm sorry, yes?
So is it a matter of getting this information out to communities? Because I know that Prince William is having issues with the community objecting to new data centers. So how are you getting this information out to where it needs to go now?
By talking to people like you.
So,
Your
Actually,
emissaries.
if we solve our electric problem, they don't need to go to Prince William.
Yes.
They'll
Let
stay
me just state for everybody's benefit, we are recording this and it is going up on our YouTube channel. But we recorded it more so because I want to send it to our local elected officials so that they understand this. As chairman of Loudoun County, I am so grateful we ended up developing the data centers here in Loudoun County because they helped us budget-wise tremendously. I'd hate to see what our tax bill would be today had they not grown, because the office market was pretty much dead, and et cetera. But we're out of space in Loudoun County. This allows us to create more data capacity in Loudoun County without having to chew up the land that the current data centers have. This allows us to expand without having to worry about additional transmission lines from Dominion to get power to them. This allows us to expand without having to worry about additional water resources. That's what I see the beauty in this for a Loudoun County.
Any of the counties around here.
So, yeah.
So if we could, since we've talked about a lot of different things and sort of highlighted a bunch of things, we'll go through this presentation deck, but not to go through each slide and kind of read off it, but just to recap some of the things we said. That way, when you see it, you can recall some of these things. So this is what an immersion tank looks like. We've embraced this entirely. Again, it shows the PUE efficiencies that are on here. Again, that's power utilization effectiveness. How efficient is your cooling system relative to the power you're using to power your servers and storage?
And how big is this?
That is a 42U. So if you're used to a rack, a traditional data center rack, 42 to 54 units, 1.75 inches. So typically you have a server is 1U. You put 42 servers in a 42U rack. This is a 42U cabinet on its side.
8 foot long.
So that 8 feet long. Yeah. So this actually can support 100 kilowatts per pod. These are called pods of heat dissipation. Most data center racks that are not hyperscalers are 5 kW. This is 20 times the capacity of heat dissipation with a PUE of 1.02. You won't believe it till you see it, so you have to come see it. This has self-contained redundant pump system in it. It's just a double wall tank, but the pump is what brings the heat out of the cooling, and then the loop goes out that little corner piece. You can cable off to the side or plumb off to the side. You can go up, you can go down. If you have an existing raised floor, you can use it to hide your plumbing, but you don't have to. This thing is best suited to just sit on a slab. So these are real numbers. Reduction in cooling costs 95%. Reduction in CapEx to build the building. You don't need to build a traditional $1,200 square foot data center complex. You can build a room like this and have your loops to go outside, your dry cooler sitting on a pad. It's that simple. So you're talking about more than a 50% reduction in CapEx for the building cost. The power reduction comes from two things. We said you're using a PUE of 1.02 versus 1.5. If you do the math, it's about 33%. So you say, why are you stretching the number and saying 40? There's another really important point. One of the biggest power consumption components of a server are the fans. There are fans all over the place, and they're whirring and whizzing and making all kinds of noise. No fans required. All the servers we use today, if it's an existing, I'll just pick a guinea pig, a Dell 740, 7 fans on the inside, 2 on the power supplies. All of them disconnected, all of them no longer functional or required. That right there is your other 10% savings. So now you're at 40% power savings, given even an existing legacy environment, disconnecting the fans. And by the way, you can put anything in these tanks. Hair dryer, literally. I mean, anything electric. They do not conduct electricity. Yeah, think about it. I mean, when there's 100 kW of electronics in there, we stick our hands down in there when we're working, and people they get really uncomfortable with that. Because there's no conductivity. It's the coolest thing in the world. 30% increase in hardware. There's no vibration. There's no fans. There's nothing moving through this other than a liquid immersion, which is coming up from the heat rising. The liquid rises to the top. The pump pulls the heat off the top. There's no vibration. There's zero dust. It's ultra clean. You're in an oil. And so because of that, it's a good portion of the longevity of the equipment. But the biggest thing is you're not thermal cycling the equipment. You're not going through a hard load, a less of a load, and the equipment is getting hot and then cold and hot and cold and fans coming on. It just stays at a really nice, even nominal temperature. So we're seeing a greater length in life of equipment. Again, that all begets better economic development when you really come down to the numbers of it all. We can. That is our demonstration room in Albuquerque, New Mexico. That is the equivalent of 80 vertical racks of equipment in 4 of these pods. And we even have them spaced out so we can show people and walk around and stuff. And this is where we're doing a lot of the experimentation with Sandia Labs, Los Alamos Labs, National Renewable Energy Labs, Morris Livermore, and a lot of this stuff is being used for ultra high density compute that is being used to do modeling and simulation, artificial intelligence and machine learning for some of the organizations, government and agencies. And we're able to do that in a very, very small footprint. Notice there's a raised floor there. That's because it was an existing data center that had a raised floor. This was an FAA facility at the Kirtland Air Force Base, and we took it over, renovated it. It was a Tier 3 data center. And since it had a raised floor, we said, oh, we'll just stick with the raised floor because it's there. We did our plumbing underneath, so it looks really clean. But if it was a slab of concrete, you'd see our inlet and our outlet pipes, and you'd see the pumps and all that stuff, which are simple, but still, they're hidden. So this also makes for hidden in plain sight.
I think I'm a little bit confused. You talked about oil.
Right.
And then you talked about a brine or a water.
Right.
Is there oil in there or water?
So in the tanks is oil.
Oil.
And it never leaves the tanks.
I mean, it's filled right up to it covers everything.
Pretty much everything's in the tanks. Think of it as a bathtub.
Yeah.
Everything's in there. There's a pump system in there, a redundant pump system that just circulates it. So as the heat comes off of it, it comes to the top and then it circulates through what's called a CDU. Think of it as a radiator. All right? That radiator pulls the heat off. Now you get to your loop. That loop is just an inlet and an outlet that goes down out to a dry cooler, which is just another radiator. We do have pumps on that, so we can create a circulation. And then we do have fans on the dry cooler outside, so we can pull the heat off the radiator if we need to. The pumps always run, because we're always pulling heat out of the tank. The CDU in the tank comes on only about every 15 minutes to pull a little bit of heat off of that, right? It's a 1 amp or less draw. The pumps that are on the cycle are less than 1 amp, and the fans that are on the dry cooler are less than 1 amp. 4 total in the system, fully redundant. Redundant pumps, redundant fans, redundant pumps in here. We never use more than 3 amps on 100 kW, 208. So that is a 1.015 PUE. The only time we get up to a 1.2 is when we're running everything full bore, and that's 2%, or 1.02 PUE. It's, when you see it mechanically, it's like, nah. But then when you see it measured, you get it. So oil stays in the tank. The loop is separate, but it's sealed. You don't consume anything. It just, once it's capped off and sealed, we need to put a pressure tank against it. It's fixed. And now it just cycles. Now it's like your car. When it's hot out, the fans come on. When it's not hot out, the fans don't come on, but it just cycles the whole time. Yeah. But that's a 400 kW data center, and it's in the size of this conference table area. 80 vertical rack equivalent, 40% less power, no water. That's the model that could change Loudoun County. But why don't the data center operators adopt this? Why haven't they adopted it? It might be a little bit of it's what you sell. It's not how efficient it is.
Power and space.
But when you get up against the wall and one of those variables is no longer available, now maybe you have to start making a change. So it's all good. Yes, sir.
The last slide you had, what's the ceiling height there?
That is the same as this.
Yeah.
Yeah.
Which I don't go in a lot of finished data centers because I'm more about the earth, the ground
Yeah.
that supports them.
Right.
But I surmise their ceiling heights are pretty significant.
Yeah, because the air,
Yeah.
what they want to do is get the heat away. Heat rises, so the idea of some of these big data halls is get that air up there to the second, third floor, and then start pulling the heat off of it up there, or move it to another room and get through a chilling system, right? But you got to get the heat away from the equipment. In this case,
Yeah.
I mean, it doesn't matter. I mean, as long as you can get the lid open and you can get the equipment out, that's your ceiling height restriction.
So
Some of our customers now too, the compute's running so hot, it is so incredibly high performance, you can't put enough water on it to cool it. You're running up against the temperature limitations of that blade. We have customers now that say we couldn't do what we're doing as far as artificial intelligence and machine learning without the immersion environment.
So there's air cooled, there's direct liquid cooling, which is when you run a manifold and you literally run the water to your CPU or your GPU processor, and that's very complicated. And that's very critical because if you have leaks in water, not a dielectric, non-conductive fluid, but water everywhere. And actually, a lot of the laboratories are standardized on direct liquid cooling of chips, and they're experimenting with this now going, oh, this is crazy. This is so easy.
even before the power challenges, land availability, which is just becoming more and more a problem. And I think it was probably 5 years ago, at least locally, one of the first data centers went, it was an 80 megawatt hall, went 3 stories, which was a big endeavor. And now that's becoming more commonplace. And I asked that silly question that an engineer might ask is, well, why not 4? Why not 5? Why not 7? And I hear that with the mechanical cooling systems that they have, they just can't build more than 3 without dedicating an entire level to mechanical equipment. So I imagine this could change that game tremendously.
What this does, this solves a problem in a tank. And now the only hard part is just getting the heat that's in that tank to a place where you can do a heat exchange. And that's the dry cooler environment.
Are the blades in that system the same as would go in a regular rack?
So you can take anything and put it in a rack. The question is, what's the best value? The best value is the highest performing servers you can get in a tank like this. If I took a 500 watt power supply based server that has 2 for redundancy, that's typically now a 500 watt supply in a 1U rack space. And I'll pick on Dell 740, 2 500 watt supplies for redundancy. You're only going to use 500 watts. I have 42 of those, right? That's not 42 kW because I'm only using 500 watts. I'm not even using all of that. It's half of that because it's redundant. So I'm only at 24 or some 20 or so kW. Now I have a cabinet of equipment with 42 of these servers in it. It's only doing 20 kW, but it's producing quite a bit of heat. And of course, I need a traditional data center for that. If I put it in here, I can cool it very, very easily. It's only 20 kW. I have the capacity for 100. So I'm not getting the best bang for my buck, but I can certainly do that. So we show immersion conversion of servers, not just data centers themselves, but servers. Any and all types of servers we can put in here. There's only 3 things we do to it. We flip it over, put the ears on the bottom. We take the fans, disconnect them, and put a fan emulator on them, which is another little trick. And then we take the paste off the heatsink on the processor heatsink, and it's replaced with a little piece of indium foil. And then we get a good heatsink. Now there's no glue or paste or anything to dissolve in the oil, and we've got a really good heatsink. So any server can be converted and put in here. We also top rack switches. You put the switches in here, you put your firewalls, routers in here. You kind of wasting the heat dissipation capability of the space, but you're making your bus, your I/O, your speed, your networking really fast because it's right there in that tank. So your top of rack switching can go in there. We run top of rack switches, 48 port 100 gig switches to our servers in these racks, and we run 800 and 400 gig connections with 2 fiber connections in here. Fiber, no problem. Lasers, no problem. Connectors, no problem. Network interfaces, remember, this stuff does not conduct electricity. And even for fiber, where you have a index matching with fiber optics, as long as you dip both in the liquid first and then you make the connection, you've got an index match, and we're doing 400 and 800 gig connections inside the tank with immersed fiber and immersed lasers. It's just, I love his reaction. He doesn't believe a thing I'm saying. Yes, sir.
So, one, how is the liquid made? Is it scalable? 2, what do you do with the liquid in 15 years when it needs to be disposed of? Right, you said 15-year lifespan. And then there's a lot about the energy efficiency of it, which is great. And we provide not only the opportunity to use less land, but also improve the design standard on the exterior of a building, which is a big issue for the community.
Right.
But like, I think the question would be, because we have so many questions about power and water, there's going to be a lot of questions about that liquid. Like, like where's it coming from, and like how do you get rid of it and all that stuff.
So the good part about, Jon Davis talked at the beginning, we started looking at immersion only because we wanted the high density compute capability that we're, for our customers, government, intelligence community, military, and its laboratories. And when we looked at 2-phased immersion, we quickly ruled that out because it is a biohazard. It is an evaporative process. It is something that is a pod that size, a 2-phase liquid immersion system. The fluid alone is $110,000. And it's a biohazard, and it is evaporative, and it's hard to manage, and you can't actually work in the environment.
Special infrastructure.
Yeah, it takes a special infrastructure to support that, because it evaporates and then it condenses. It's a complicated process. We went in single-phase immersion because of what you just described. Number one, it's a 15-year design life, 10-year warranty, and it's made by many manufacturers. It's basically like a cooking oil. It's not a cooking oil, it's basically like synthetic, but also there is a sort of a kidney dialysis capability, where you can run it through a filter and reconstitute it again back to its original very easily.
Yeah.
So if you introduce dirt into the environment, and there's a reason why I say that, if you introduce dirt and contaminants into the environment, there's a way to clean it and filter it. But as long as it maintains a specific viscosity and a specific capability of transferring heat, it can be used forever. And it can be reconstituted with a dialysis capability. The only reason this fluid got dirty for a while was, you've heard of the cryptocurrency industry. So this is really where this industry took off. Liquid immersion was people taking their S19J Pro miners and just throwing them in a fish tank and going, oh, look, I can keep it cool. I'm using all this power, but how do I keep it cool? Not everybody can afford a warehouse on the mountaintop in Colorado to try to keep their mining systems cool. They want to use a facility like here, and all these facilities say, no, this is not a good opportunity. This is not a good place for us to do crypto, because how we keep it cool, how much power you use. So they started using liquid immersion, these dielectrics, to do this, but then they burn these machines up, constantly in and out, in and out, in and out. They're not manufactured that well, dirty, and so this fluid would get dirty, and so they came up with a way to reconstitute it. That's where the process came from. We don't do any of that. We stick stuff in here and we run it 100%. We don't touch it. We haven't touched the stuff in New Mexico in 13 months. And it's pristine, it's clean, the viscosity, we have the fluid tested every year. There's a testing process, and there is a supply chain. This is a synthetic man-made product, and so it is well documented, patented, and as far as I know, it's going to change the industry.
So synthetic, is that equal
It is synthetic.
oil, like out of the ground oil, or is
No,
it
like a cooking oil. It feels like a cooking oil.
But is it
like a
what's
vegetable.
what's the base product?
I can get you the material sheets on it if you're really interested.
I am.
but
Because
yeah,
I think that
yeah.
I think so much of the conversation is
Yeah.
everything Luke says absolutely right. The closer you meet it to one, right?
Yeah.
The better. But there's always going to be that supply chain of like, where's all this other
Yeah,
stuff coming
yeah,
from,
yeah.
and how what impact will that have on?
Well, there's no such thing as perpetual
Yeah,
motion, right?
yeah.
So something's got to give.
Yeah.
What is it about this that's giving? Sorry.
Me? I mean, it reminds me a lot about Volkswagen and what they're doing in terms of their e-vehicles and their partnership with Northvolt and ADACEN, right? They're trying to look at how do you make these batteries in the end go through a life cycle where there's only 1% waste. So would you call this, that like 1% waste goal?
I think it's gonna take a long time to get to that, even that percentage. This is a patented fluid that has longevity, and you're not disrupting anything. Only variable is heat in, heat out, heat in, heat out. There's no contaminants, there's no oxygenation, there's no degrading, there's no evaporation. And the whole thing is contained, and then the loop that cools it is contained. It doesn't get much simpler than that.
That's awesome.
I don't, we can give you all the statistics. This is not brand new. This is over 10 years old, this type of technology. But what is really brought it to the forefront is the problem you're experiencing. You need to get more power efficient environments. Now all of a sudden this makes sense. And also the density of those servers, once again, is to the point now where there really isn't a choice.
The other question I had was, obviously, huge applications to, what you've outlined, utilities, DOE, defense. But I came from Palantir Technologies before I was here, so I was selling lots of edge computing.
Mhm.
What are your other industries you're targeting outside the ones you've listed here? Because I see so much
Pharmaceutical?
application. Yeah, pharma.
To be able to put AI, I'll use the term AI, ML, mod sim, right? Artificial intelligence, machine learning, which are different. Modeling and simulation, which are different, but those four aspects require ultra-high performance computing and the ability to do near supercompute capabilities. We can do that now at the edge. So now think about where decision-making at the edge becomes really important. It becomes important in our air traffic control system. Just so happens to be, there might be some projects in that area. It happens to be important in pharmaceutical development. Our DNA was used to create some of the vaccinations. A lot of that was simulated, right? If you look at our national defense, a lot of that stuff is simulated. What happens if this happens? Model it, simulate it. So now start thinking about cars, autonomous cars, self-driving cars. Decisions are being made at the edge.
And that's the reason I asked the question. My main clients were life sciences and health, right? So I know exactly
Big
why
frontier.
that needs to go there. But I'm also thinking about, as we continue to diversify our economy in this region, how can we be more attractive with this kind of technology? And I think manufacturing is a huge area. Obviously bio fits in there, but there's other places where
Full
this
materials development for the manufacturing.
huge sense.
I hate to say it, but it's a given. Financials,
Yes.
right?
Energy services.
Biopharmaceutical, our DNA, all that synthetic processing. Of course, in our national defense, I hate to use the term, but if I use this term, it might make sense, but sentiment. What is the sentiment currently of a person, a region, of a situation, and how you can calculate that takes in a lot of sensor data. General Davis was very instrumental in the F-35 program, and I won't say any more than I've heard publicly, but there's a lot of sensors on that particular airplane. Edge computing is becoming more and more important. So, I mean, the data centers are immensely important to where it all comes together. But at the same time, look at the power grid infrastructure. That makes your network a critical component of the power grid. Not your power network, your network, your information network. Well, now if you can do more autonomy and autonomous type of decision making at the edge with supercompute capabilities, which is only available when you have the ability to do high performance compute at its limits, then you need a little environment in which you can actually host that. So this just all creates, it's just another piece of the puzzle, but it's about the efficiency, and this is why the DOE is so critically important in this, because they're really concerned about the water, the power, the space, and things like that.
And we had a visit about 7 months ago from DOE. They called me and said, "Hey, who you are?" I'm like, "Yeah." He said, "We have your pitch deck for your company that you're involved in. Could you come talk to us?" And I did. And then they said, "Is this real?" I'm like, "Yes. We've been doing it. Self-funding company, but we felt that we had to prove this technology."
Yeah.
We've been operating for 13 months now in a data center that we funded, and every piece of, I would say, vaporware on the slide is actually proven to be 100% accurate. His previous life said no lightning bolts unless you can do it. Right? No lightning bolts in my slides unless somebody's actually done it. We've actually done it and proved it. So it's some pretty hard graders, Sandia, Los Alamos, National Renewable Energy Lab, have come to us and said, "Hey, this actually works." And so the Department of Energy said, "Hey, we're actually going to be an advocate for your technology to try to help you transition." So it's been, honestly, pretty interesting. I would say looking at Loudoun County, what your task here is, I think, is how do we grow this data center business, given we've been given a finite, asset, which is our energy. Just like Bob said, this is the way to do that. So it could also too, it's like, you've got, because of the reduced space required, you could actually put more clients in the same facility, higher 1/10 the space, 33 to 40% less power, no water use. So environmentally, it ticks off a lot of buttons, but also too, maybe allows for more clients to go in a set facility as well.
In this particular slide, I want to point out a couple things. The density, 13,680 CPU cores, 12,288 GPU cores, 120 terabytes of cache, 400 gig of switching fabric. When you put all that together, you start to get things like 40 and 50 and 60,000 core pods. Now you're talking about traditionally what it would take to do a data center in pods, because the ultra high density in the ultra small space. You have these two different orders of magnitude feeding each other in the opposite direction. One is significantly small, the other is significantly greater capacity, and you put those two together and you get astounding numbers. We go to the next one. As an example, in this particular one, this particular environment is 50,000 cores of CPU, 45,000 cores of GPU, and it's a bunch of cache storage. But this particular one is the compute composition within this. That is, again, more than 20 equivalent racks of the compute equipment, but it's 20 equivalent racks of power for compute equipment, but it's probably 4 or 5 times that in terms of the density compute. This doesn't mean a lot to somebody who's doing co-location in a particular data center here, but it means an awful lot to the scalers that are doing lots of customers in the smallest footprint possible, where now their costs are lower, capacities are much higher. We go to the next one. This is an example of storage. Intel has a new form factor for storage. Storage becomes a very large consumption consumer of space in a data center, but not the biggest consumer of power. It doesn't need as much cooling, but it just becomes a big arena of space. With the new form factors and the ability to put them in liquid immersion as what's called solid state disk, you've heard of, thumb drives are solid state, you can now do up to 42 petabytes. 42 petabytes of storage in a 42U pod, because you can keep it cool at 65 kW if we can do 100 kW all day long. What that means now is you've now taken what would normally be 100 rack equivalent of storage for 42 petabytes, and you can do that in a 4x8 pod on the side. It's you have to see it to believe it.
And we're doing it.
And we're doing it. The next one. So this is basically what you do. It's 200 regular air-cooled racks and 20 of these smart pods. That's the simple math. It's a 10-to-1 ratio. And then start imagining the space, the real estate, and then the footprint of the building, the height of the building. Doesn't have to be any taller than the ceiling. Doesn't have to be any kind of a different building than this kind of building. Now you're talking $150, $200 a square foot construction versus the 1200s and the 1400s.
No noise inside that facility either. Doesn't make
Let's go to
any
the next
noise.
one. So what's nice is these are renderings that Sandia is doing for us for typical data center, and I'm saying typical, 100,000 square feet, 10 megawatts, $100 million to build before you put your first server in it. These are 30,000 square foot facilities designed half for people, 15,000 square feet for immersion, and we're talking 30 megawatts with that amount of space. So 3 times the density in 1.5 times the space of 1/10 of the space, because we're accommodating people. It's a whole new dynamic to how you build these things. Again, you can convert an existing facility. If you have the chill plant, why not use it? But now you're using it more effectively. Also, forward deployed theaters. 40-foot Connex box into these pods. You now have an 800 kW data center in a Connex box. You don't need anything other than a place to put it. The dry cooler sits on top, doesn't use water, it's just that loop. It doesn't use consumable water, it's just that sealed loop. And of course, you put a gas system in there for fire control, even though nothing in the pods can catch on fire. It's only for the human factor, right? And then if you really want to, you go forward deployed, you have a generation system, your dry coolers, and you have a whole bunch of pods, and you've got yourself a 2 or 3 or 4 megawatt data center in the footprint of a 40-foot shipping container. So this is the military / Department of Defense aspect of this, but this is how far this can go.
Dealing with a bank in a country in Africa that's stable, that wants a data center backup. It's another one that one we had bid on, but it's a second one that just popped up. They're asking for the containerized version, so they can get that in 90 days. And it's basically, everything's put together. It's waterproof, it's got a locking door on one end. You plug it into power, it would be 800 kilowatts of power, and you basically have an 800 kilowatt data center with, it's 8 times 20, so it's 160 vertical racks capability on a 40-foot long ship.
What's delivery time, once an order is placed?
Various pods, the 42U one we use, 2 weeks. The mega pod, which is the larger ones with there's either a 10-foot, a 20-foot, or a 40-foot version with either 2 pods, 4 pods, or 8 pods in it. That's about 4 months. They're custom built. And then this is about 4 weeks. This is the micropod. This is literally a 7 kW data center in a box. Everything included. This is what you put in your closet. This is what you put on your rooftop. This is what you put in your cell phone tower. And we're currently deploying these in substations for power utilities to give artificial intelligence capability, machine learning capabilities at the edge for sort of the next generation smart grid.
And now a law firm.
How many of
Bring
those
it
do you
up.
have? How many of them have you placed?
They don't want to get hacked.
I can't tell you how many.
Private cloud.
We have a contract right now with Power New Mexico, the PNM, New Mexico Power Companies.
I'm gonna
And
jump
we've
in
done our
back on
first-
this for a second.
We've done our first pilot with 7 units, but they have 220 substations we're deploying these in. So we'll eventually deploy 220 within the power grid. It's every
And you're-
substation,
But you're saying that you're self-funded.
yes.
How do you make that many being self-funded?
We do not manufacture this. We are the leading integrator of this. We are a consumer of it. We are a customer. We're here to share with you that we decided to build a more resilient infrastructure. So we picked military bases. We picked under controlled airspace. We picked pre-grid power capabilities. But when we started to build the facilities, we took a fresh approach and said, how can we be the most efficient possible? And we looked at all the different technologies. We decided to work with liquid cooled immersion. There's several manufacturers of liquid cooled immersion systems. There's 2-phase, there's single phase. We chose single phase. So we don't hold the market of this particular piece of hardware, but we are the leading integrator in the US of adopting it and working with it. And now we have the blessings of Sendia Labs and Department of Energy and things like that. to go
What
ahead and
country
build.
does that come from?
It was originally started in Madrid, in Spain, but now it's being manufactured in West Texas. There's a new gigafactory in West Texas where these are being produced because they're very, very popular amongst our group.
How many people in a facility are needed to run everything?
Less than a traditional data center. You mentioned all the complexities. Think about the chilling system, the mechanical folks. You still have switching gear. You still have UPSs. You still have your power systems. You just use less of it, but you don't have the complexity of the cooling systems. You have some cooling, right? I mentioned pumps, I mentioned closed loops, I mentioned dry coolers, but they're all benign. They're all very, they're just, unless you get a leak, right? And then there's no panic if you do. You've got a little bit of time to redirect things, so. Yes, sir.
Oh, maybe you're gonna get this. Will you discuss how you're gonna fail to the grid, like how you generating power?
Yeah, I can talk a little bit about that.
Okay.
But on our campuses, like in New Mexico, we have a 570-acre campus that is generating power, different types of power, for experiments at Sendia. We have our data center campus, which is on 25 acres, which is 16 buildings that are being developed, the first of which will be 30 megawatts. So of a 150 megawatt plant, 30 megawatts all being developed on campus. We have a private substation with a power company, and we have an interconnect agreement, and we have pre-grid infrastructure. And what happens is we're running on our own power, but if we fail to the grid. That's our third source.
Right.
2 renewable sources, one very renewable, the other not so renewable, but still checks the box. But that's not our goal. Our goal was just to be self-contained. And so we have a facility in California that has a 140 megawatt geothermal plant. It's been running for the last 30 years. It's been down 2 seconds in 30 years. Very reliable. If that fails, that's our primary source. We'll fail to SoCal Edison through a substation. So that's our failure. So instead of running on the grid, and then when there's a failure like in Texas, we worry, are we gonna get that diesel fuel truck delivery? Are we in the high priority of that contract, chain? We don't have to worry about that. We go the other way. In Ellington, Texas, in Houston, over 100 billion cubic feet of natural gas gravity fed to our plant, so we will never run out of natural gas, gravity fed. So we're very comfortable, our power will always be resilient there. So different places in the country, hydroelectric would be a source of secure local power because of the campus environment. Geothermal is in some locations, solar is in some locations, natural gas in some locations, and there's some countries right now that are experimenting with SMRs, small mobile reactors. Again, think about it. We want to have our own power, run our own systems, be more efficient, be very secure, and then if we need to, build the grid, or even if we're just testing.
No windmills?
We're at airports because of our nature of using aircraft for moving data. Because we're at military fields that have airports, we can't have windmills.
Okay.
I'm just
Okay.
curious to help me understand the physical size of this, roughly what are we looking at?
That is about 3/4 the size of this table. It is about 50 inches tall. It's about 3 inches deep, and it's about 4 feet wide. And it has 7 rack units of liquid cooling in the right-hand tank, but the left-hand side is its tricooler. In this case, it's a heat pump because it's all standalone. This doesn't have the same PUE. This is 1.04. Not 1.4, 1.04. Yeah, it really is. So we are about building more resilient data centers on military bases, secure airspace, with a different type of networking that just so happens to have a depth to what we're doing, which is ultra-high efficiency. So we can support ultra-high compute. Those are the problems we had to solve. How can we do ultra-high performance in the smallest footprint with the least amount of power and no water? And that's where we decided to put all this together. The benefit is, from what we've learned, is you can get more power out of what you can get more use out of the power you have if you just are willing to make the conversion. And it can be done modularly, just 100K increments.
Yeah, where were you 5 years ago?
Figuring all this out and trying to get permission to use the land on the military bases. It took a while. Data Oasis is what we call these secure campus environments that have those 3 elements: the pre-grid power, the physical security, and the airspace capabilities. But then again, the depth to it is this efficiency. And we keep saying the same thing over again: less water, no water, less space, and all that. Let's go to the next one. People say, well, what can you put in here? You can put anything in these pods. You can convert any standard server, any appliance, any piece of hardware. And by the way, with the utilities, there's this approach of having a lot of hardware appliances out in a substation. I'll pick one as a guinea pig. A Nokia SAR, service aggregate router, is a very popular piece of equipment to sit in a substation. Now Nokia is working on virtualized software capabilities so that you no longer need their appliance, you just run software. Well, what do you have to run software on? Servers. You'll put a server in a substation. It's a disastrous environment for putting things like that because they're just really dirty. They're outside really. There's lots of power, whatever. And so now when you put a micropod out there, you have the ability to run 100 virtual servers in a micropod. You can do weather anomalies, you can do telemetry gathering, you can do decision-making, AI, ML, mod, SIM, and you can do things like virtualizing all of your appliances in an environment that now is one unit. You just have a bunch of those, you just roll them in, reload the configuration, and you're off and you're running and your maintenance is lower. Make sense? It's so simple. Maybe we're like the laziest people you've ever met.
Clearly.
So there's some specific manufacturers that are building hardware just for this capability, which absolutely positively can go on an airport data center. When you get 10 kilowatt servers into you, do the math. You start seeing data center requirements. Economic development in all the different regions we work, they constantly come to us and go, hey, we got this data center company that wants to build here, but they want to go to really high densities, 40 and 50 kW. We go, okay, it's easy. They're like, well, no, they're terrified. How are they going to get there? There's no water here. There's no this, there's no that. It's like, you don't need it. Just build them one of these. We've helped a lot of economic development groups land some new server companies, new data center companies into an environment because they didn't know they could do that. So, does this all sound believable, or do we sound like we're full of it and you got a big ego?
That sounds credible.
Okay, you got to come see it though. The first time you have 100,000 watts in a tank and you put your hand in it, It goes against everything you've ever seen, and if you really doubt us, I'll put a hairdryer in there while it's running. And if you really doubt that, I'll take a blowtorch and I'll put a flame on it and it won't light. And you're just like, okay, this is different. Yes.
You may have mentioned this earlier, but how many gallons of oil in
Can
the
I
car?
ask a question? This is Georgia, by the way.
Hi, Georgia.
Thank you all for being here.
No, you can't, you're not allowed to, because that COVID thing, you know.
Oh,
Yeah.
hold on.
Just
6 feet.
Just a second, let
Poor
me put
thing is
you up there so we
quarantined,
can
it's
see
bad
ya. There you go.
Hi, Georgia.
Hi,
Hello,
Georgia.
everybody. Thank you all so much for being here, and especially to John and Bob for this incredible presentation. Where can we go to see this? You said come see it. Do you have something in the Washington area where we could go on a trip?
If I need to say Albuquerque, New Mexico, so if somebody really wants to take a trip out there, then I'll say Albuquerque, New Mexico. But you can take a trip to Silver Spring, Maryland if that's more convenient.
But Albuquerque
I'm
is
sorry, I
more
didn't hear
fun.
you. Did you say Silver Spring?
Yeah, Silver Spring, Maryland, yes.
Oh, that would be fantastic. We should plan on doing that.
Yes.
Certainly, some of the people that have attended.
Albuquerque sounds more fun.
Yeah, next time go see Silver Spring.
You can go to the airport.
Yeah.
Let's do a day trip.
That's right.
I'm sure once
They have a corporate jet, you
Come on.
Supervisors, special
Yes.
representation today from Prince William County, that this is something that is going to be extremely important for them, because this is a big
Yes.
topic of discussion right now in Prince William, so
Right.
we're very grateful for you all coming and do this. Thank you very kindly.
Thank you, Georgia. Appreciate
Well,
that.
actually, the Washington Post has just done a couple of big articles on the controversy in Fauquier County, right outside a town called Warrenton.
Yeah.
Where, and Fauquier is just huge on conservation, preservation and such. And they fought the hell out of this thing, yet the planners still look like they're going to approve it because, it's zoned for industrial, which I assume that's what these data centers need to be zoned for. And
That's
it's
the whole point,
passing, but
no?
if they had your argument,
Right.
and this is Amazon Web Services.
Right.
Yeah, I know it would have flown a lot easier.
Actually, I think, in thinking question of zoning, since they don't need the power grid
It can be
and
anywhere.
the other utilities, you could put this anywhere.
Oh, is that right?
I mean,
Put
from
this
a
building,
logical
yeah.
planning standpoint, why wouldn't I have this next to an office complex or another non-industrial complex where we're putting data centers now, rightfully so because of how they are currently designed, et cetera. This could go in the backyard or behind the neighborhood even, if it is truly quiet and you don't have to have the minion run the tower to it,
Yeah.
transmission lines.
Huge tables. yeah.
This is a much more distributed environment, if you want it to be. Now, you can make much better use of a consolidated environment.
Yeah.
You can take advantage of it that's already been invested. That way you don't go to your data center community and say, you've done it all wrong, you've got to completely retool. No, just take those 45-degree loops and take them up to 75 degrees and start converting these on some of those chilling systems. And you've got yourself 100 kW pods, and you've just given them 40% more life out of the power they
Quick
use.
question. How does this all translate into dollars? What is the business guy, asking? When you, for instance, let's say you make a pitch to an emerging conversion prospect, right?
Mhm.
Are you able to go in and say, you've given us a lot of expense lines right now in terms of savings? What's all that add up to? Like, let's say it's $1 million a month to run a data center, and I have no idea whether that's even close, but how much savings is that customer going to realize in the bottom line?
So the savings are relative to different things. If I were to say to Facebook, you don't have to do 400 or 500 million gallons of water a month, how much savings is that? That's relative to the water. If I say to them, you can use a PUE of 1.02 and you have a third less power for your hyperscaling activities, that's a third of that power. The data center companies charge for the power consumed as a pass-through, but then they charge that PUE tax. That's part of the reason why they don't want to make this conversion. Because now their bills just went down by a third, right? The PUE is less. But also, they have to make the investment in this infrastructure to be able to save the customer money. Why would they want to do that? So it's kind of a harder sell to somebody who's already made the investment in a chilled plant to say, now you don't need to use all that, you don't need to charge the customer for that because you're being much more efficient. it just wouldn't fly until you hit a variable, which is you can't have any more power.
Like we have now.
So that's why if you haven't heard of us, we're out here doing this without needing that in the first place. 5 years ago, we started this. We started 8 years ago finding and getting permission to use the facilities. We started developing this with the laboratories, and we started using it 3 years ago, and we started in production 2 years ago, and we got our first customers, and we've been running and operating in production for the last 13 months. To all these numbers, yes?
How does it work if you have a data center in Texas, you have a data center here in Loudoun County, and you also have a data center in California? I know that there are some companies that they have them in those areas. How do you set it up so that the data centers can talk to one another?
Well,
Am I saying that correctly?
Absolutely. Well, this area is famous for its exchange. That's what created all this. The data center wasn't the beginning of it, it was the result of the exchange.
Right.
That was the beauty of it. Have a place where all the information can connect, right? That exchange is what kind of began being close to that exchange. So we do use terrestrial fiber connections between our facilities. We also use a product and a capability called quantum safe encryption. We actually run our connections across fiber a little differently, and we also show people how to do that, where we actually protect that data so it can't be harvested, because you know there's adversaries right now that are copying everything that's going across fiber. Very easy to do. It's encrypted, but they go, we don't care. We'll use this new thing called a quantum computer, and we'll figure out how to decipher it much faster than you would have imagined. And this is the real threat today, is encrypted data isn't as safe as you think. So what we do is we move our data encrypted, but we move the keys a different way. So if you capture this data encrypted, you'll never, ever, ever, ever be able to decrypt it. This is a whole other subject, but quantum safe encryption is the new way of doing that connection that you talked about. There's one more piece of real quick. Remember I said we're on airports? We're moving very large volumes of data via aircraft. Very large flying thumb drives. So we're moving data like this between our facilities, and that's why we built our facilities on airports. By the way, one of our target facilities and sites is Dulles. Not Ashburn, Old Ox, but inside the fence, in the controlled airspace, on the property, with our own power capability. Everything I just talked to you about, there's a model that we developed for Dulles. Just so you know. Did I answer your question?
It did. Now I have one other question. A couple of years ago, a couple of data centers here, and how do I'm trying to see, they ran cables underneath the road, and someone cut the power, the fiber optic cables.
Happens all the time.
Is that it? Okay, so is that information still protected? It's not lost or anything like that?
The connection's lost. That's why you always have to have redundancy. You have to have, like an emergency services IP network that's called FirstNet, has a fiber infrastructure and a microwave radio infrastructure. The two have to work in harmony, so that if you have a problem, you don't lose connectivity.
Okay.
You can add satellite connectivity to that. You can use wireless connectivity in different forms to that. There's all kinds of different things, and if you talk to Jon Davis about that, he'll tell you there's some unique things going on in communications infrastructure, but also, remember I said the power grid is moving to an edge compute capability?
Yes.
Because that network is so vulnerable that if you cut it, you now put an entire substation and an entire region at risk. But if that region can now make its own decisions on what to do and how to balance itself, now you've changed the game. You've made a more resilient grid infrastructure, and the network isn't the critical piece.
Okay.
So there's a lot of dynamics to this. You'd asked about how much fluid? 275 gallons in the large tank, 1,800 pounds. The tank's 800 pounds. When you put it all together and you put it on the race floor, it's 80 pounds a square foot, so no problem with an existing race floor. Two-phased immersion, Two-phased immersion, 20,000 pounds, 4 pedestals, 5,000 pounds in a space that size, only can go on a concrete slab. So forgive me, don't even talk about two-phased immersion. I hate to be negative to that industry, but its days are gone. 3M was the exclusive manufacturer of the fluid for two-phase immersion. They just stopped. They said, this is not a good market. This is not a good product. This is a biohazard. This can't be maintained. It can't scale. The supply chain isn't going to work. So it's not a viable business for two-phase immersion. Did I answer your question? You did. Okay.
Are there any possibilities of having unmanned facilities?
Absolutely. Absolutely. I mean, think about the autonomy capabilities of something that is also irrelevant if it needs to be. So the smaller you put edge computing out there, and the smarter it is, also, believe it or not, the more expendable it can be. Right?
How so?
Yeah.
Well, you're
I
talking
wanna
work. Okay, take a ship, maybe a military ship, maybe under one of the branches, and you do immersion cooling capability on that. You have a natural heat exchange by just going through a radiator on the sea. So now all of a sudden this becomes a really nice. There's a lot of compute capabilities on today's naval fleets, a lot. And there's even might be a logo on one of those slides that it's doing a lot in that space. And this becomes the best way to cool that. Because again, the densities are getting so great that you don't have a choice soon if you want to be with today's highest performing servers. You don't have a choice if you're running out of power. You don't have a choice if you can't use water. It's all coming to this liquid immersion environment. We just happened to decide to do this, and we've had such great result, we can't help but share it. We were asked to share it here. We're not trying to compete with any of the data center companies. If anything, we're trying to help them convert. But that's not our business. Our business is DoD, DOE, agencies and things like that to support a more resilient kind of campus environment. It just so happens that this is a really good kept secret.
And to me, this gives a Loudoun County or even a Fairfax County the option to expand when you're running out of area to expand your typical data center market. And even for the new places that want to capture this, or companies that may want to go in that community, this gives an option that I think helps solve the problem of those that don't want to hear the noise when they open their windows in the summer. They don't want to see the transmission lines having to go in. And if you don't have the water resources, this gives that option to solve three problems in the community and provide for data-centric facility in your community. So, folks, we are running on the, getting close to 1:30. I want to thank both General Davis and Bob for coming today and sharing this. And I learned a lot, so I certainly appreciate it. Georgia, did you want to say any closing remarks?
Also, kudos to both the General and to Bob for being with us, and thank you for such a informative presentation. I'm sure lots of good will come from this. It's just the beginning of working with us, because we'll connect you and help you as much as we can with our local business leaders and so forth. But I also would like to let everyone know that our next meeting is March 28th, and is Rich McCary there?
Yes.
Rich, you want to tell them about the jet aviation event?
Well, on the 28th, we're going to go to a tour of the revamped facilities of Jet Aviation. I think you gotta let Scott know, and then we need to give them a number as to how many are going to attend, but that's same time as this, March 28th, and should be, since they've revamped everything, should be a pretty good tour of their facilities.
We'll follow up with them later this afternoon and find out what our
Capacity
numbers will be
is.
of the total. We'll get an email out to everybody. But you and Georgia are going to need to work on that, because I'm out of the country for 2 weeks next month, and
all right.
so I'll be limited in email capacity.
We'll handle it.
And I don't want to get on the computer, to be quite frank.
You should tell everyone where you go with Scott and why.
Well, going to Japan to see our youngest daughter, who just had her first child, our 14th grandchild.
Congratulations.
So I have pure American grandchildren. I have New Zealand grandchildren. We now have a Japanese granddaughter.
If you go to Tachikawa, please take pictures, because I was born there and I don't remember it.
Grandchildren born in Japan.
Oh, wow.
Well, thank you, everybody.
Thank you.
I certainly appreciate the attendance today. It's good to have everybody here. It's just good to be back from COVID.
Oh, yeah.
This is
Well, not for
truly-
Georgia.
Except for Georgia.
Oh, I'm
Georgia.
sorry. Poor Georgia is
Georgia.
suffering from, got COVID over the weekend.
Last
That's
one.
such a
Oh,
good
really?
thing here. So.
Yeah, I'm not doing what you guys. Okay.
Great to see you.
Thank you.
Thanks, guys. Everybody.
Tune in your-
Go ahead.
Before,